Thank you for the invitation and the introduction. This is joint work with Eric Hanson. There is an archive number there that will pop up at the end if you're curious. So we only have 10 minutes, so let's just go into some background. We're going to work with a skeletally small abelian category. We just don't want too many isomorphism classes of objects. And here is sort of the anatomy of what a composition series looks like in the way that we're used to. So you take some object, you take some sub-objects, and as a reminder, I'll say this throughout the talk, sub-objects have maps. They're not just objects, it's the object and its inclusion. This will be important later. But you have an object with a bunch of strict sub-objects, and you can also point out the length if you're looking at length categories. And we're going to think about multi-sets of subfactors. So xi mod xi minus 1. And for composition series, of course, we want these to be simple objects, which have no sub-objects of their own. And so the classical theorem that we'll be trying to generalize is that if you take two different composition series of the same object, they have the same subfactors with the same multiplicity. So this is an equality of multi-sets, same elements, same multiplicity of those elements. So this is the classical result used all the time, implicitly, explicitly in representation theory. So we're going to fix an object for pretty much the whole talk, except like the last slide. And we're going to talk about sub-object chains, but we're not going to do these finite chains anymore. We're just going to take some totally ordered chain of sub-objects, but it does need to be ordered by inclusion. So remember, sub-objects have maps, so all these maps play nice with each other. And then we want the lowest object to be 0 and the top object to be x. So this is exactly the type of thing that we want. And then when Eric and I were doing this, we started with just a sub-object chain, and then we said, okay, what assumptions do we need in order to make this work? And the first thing that you need is bi-complete. So you can take any totally ordered subset of this delta, and what you need is you need the limit and co-limit of that to exist in your category. And remember, because we're talking about objects with their maps, this taking the limit and co-limit, this makes sense because whenever you look at some subset of delta, this is actually a directed system in your category because you already have the maps. And we also want those limits and co-limits to be in delta. It wouldn't do us much good if they existed, but they weren't part of our totally ordered set. And then we can look at some other bigger or more dense sub-object chain, however your mind processes this, but we call it a proper refinement if it strictly contains delta. And so this is just sort of this is just a generalization of your sub-object chains, and you need the bi-completeness in order for things like composition series to work. So take some bi-complete sub-object chain, and we can define this object. We know this co-limit exists now. We can define this object y minus, and what you do is you take everything below y in your chain, and then you look for whatever the next thing is supposed to be. Sometimes that's y, and sometimes it's the predecessor of y, if y has a predecessor. And then now that you have this y minus, you can look at all the subfactors of your bi-complete chain. So it's all the y mod y minus, such that that's not 0. So all y's with a predecessor, and then you look at the quotient. I'll just point this out now. It's possible that this is empty in certain situations. And so we can talk about whatever a composition series should be, and it's a bi-complete sub-object chain where all the subfactors are simple objects. So this makes sense. And then you can talk about what it means to be subfactor equivalent. You have to be a little bit careful with this, though. Your subfactor equivalence needs to be a bijection on objects in your chain with a predecessor, which is a little bit stronger than we're used to, but it turns out this is required in order for this equivalence to actually mean anything. Yeah, pardon. Okay. So I know lots of definitions. So X is sub-object bi-complete. So now we're moving away from a particular bi-complete subchain of X and talking about X as a whole. And so if you take every totally ordered set of sub-objects, then the colimit exists and is a subobject of X. This is not always guaranteed if the colimit exists, by the way. And then the limit exists and is a subobject of X. That will always be true. If the limit exists, it will be a subobject. But for the first condition here, JHS1, we're calling it, if the colimit exists, it may not be a subobject. So we're requiring these exist and be subobjects of X for any totally ordered chain of subobjects that you take. And so these are the first two conditions that we'll need for you can see the title of the slide, what we call weakly Jordan-Holder-Schreier objects. And so the first theorem is about composition series. And so if you take some subobject if you take an object X that is subobject by complete, then you get composition series. So X has a composition series. A subobject chain is a composition series if and only if you can't refine it any further. This is good news. You shouldn't be able to split simple factors into something smaller. And if you take just any totally ordered set of subobjects, it exists inside a composition series somewhere so that you can refine it until you get a composition series. So this is the behavior that we're used to seeing in the finite case. Okay, so you saw that these two assumptions are labeled JHS1 and JHS2. So let's keep going. And you take some bicomplete subobject X, and then you look at one of its totally ordered chain of subobjects and some other subobject Z, and we need these to play nice. And so the two requirements we have are the colimit of this set is equal to the colimit of delta intersected with Z inside of X. And so this set on the left, Y intersect Z for all Y in delta, it's exactly what it looks like, but this is also totally ordered by using properties of limits and colimits. So you can look at the colimit of this because of the assumptions on X. And then you need something that's not quite dual, but is similar. You need to be able to take the internal sum inside of X. So you can think of this as the image of the direct sum. You can think of this as the internal sum. If you're used to modules, there's a way of doing this element-wise. But you need to look at all the chain of Y plus Z inside of X, take that limit, and that needs to be equal to the limit of delta, and then adding Z afterward. And so remember, subobjects have maps. And so this equality here is actually an equal sign. It's not just an isomorphism. So we need these to be the same object with the same inclusion into X. And now there's this word weakly here. And it turns out if you want to remove the word weakly and talk about Jordan-Holder-Schreier objects, you actually have to assume that a composition series has factors. And so there's a way of obtaining these composition series that have no factors whatsoever. Ask me if you're curious about a specific example, but I'll just tell you this is possible. And so the theorem is if you take a weakly Jordan-Holder-Schreier object, it has composition series, and all the composition series have the same subvectors. So this is a JHS 1 through 4 are sufficient conditions to give you a Jordan-Holder-Schreier like theorem in your abelian category on X. And so you can do this for each X individually, or you can just assume that every X has these properties, and then you get even more structure. And we can use this notation, subfactors of X, when X is weakly Jordan-Holder-Schreier, because now it doesn't matter which composition series you pick. Okay, last bit. So we're going to write JHS to save space. And so if you take this is a very strict requirement, but if you take a category where every object is weakly Jordan-Holder-Schreier in both A and A op, so you have to look at the opposite category as well, then you can look at short exact sequences, and you get an induced bijection on your multi-sets of subfactors. And it's the subfactors of Y and Z are actually the subfactors of X, and this is what we see in the finite case that we're used to looking at. And if Y and Z actually have subfactors, then Z is 0 if and only if the subfactors of Y are the subfactors of X. So this is what kind of generalizes a length category. It looks like you need some pretty strict requirements to do so. You have to have weakly Jordan-Holder-Schreier in both A and A op. But in a length category, this is like automatically true. Right. And so then just a handful of other results. If you look at proof for modules, they're JHS. If you look at countably generated modules over Artinian rings, pick left or right, whatever is your favorite. Those are JHS. And then this is kind of a fun one. If you take pointwise finite dimensional persistence modules over a poset category, you can do this a little bit more generally, but poset categories are easier to state in a slide. It's JHS, and the subvectors are actually given by the support of X inside your poset category. The multiplicity of each factor is given by the dimension of X at each object in C. So this is not surprising, but now it's nice to know that it is actually true. And so a lot of you know I work with continuous representations. And so really the goal of doing all this for me was to get to this last bullet point and look at continuous representations, which are persistence modules. Thank you.